In these notes, we're going to be looking at exponential functions. And so we're going to start with sort of a base graph, and we're going to look at the graph of y equals 2 to the x. So this is exponential because there is a variable in the exponent. This is different than our polynomials, which just had degrees. There's a difference here. So our exponent is the one that changes. If we wanted to graph this and we didn't have a graphing calculator, remember we can always do that by just plugging in some points. When you do that, if you want to sort of test a behavior, make sure you plug in negative points and positive points. So let's plug in maybe these 5. So we plug in -2, we get 2 to the -2nd. Remember that negative exponent is going to make this 1 over 2 squared, or 1/4. So we've graph that. It's like here. If we've got -1, we got 2 to the -1st. It's just 1 over 2, or 1/2. It's going to be right there. To the 0, we got 2 to the 0. Anything to the 0 power is 1. Remember that. That's going to be important later this unit. So that means we're at 2. We're at 1. And we've got 2 to the 1st power, which is just 2. And then 2 to the 2nd power, which is 4. And so now we can sort of see our graph take shape. And we're just going to connect. And so if you want to think about what happens as we go to infinity, or rather negative infinity, well, if x is going to negative infinity, then this is just 1 over 2 to the x. Can this ever be negative? No, it can't be negative, right? Because we don't have any negatives anywhere in this expression. This is just 1/2 times itself a whole bunch of times. So this is never going to be negative. It's also never going to be 0. Because the only way to get 0 here would be to have a 0 on the top, and the top is a 1, so it can't be 0. So this is going to end up doing sort of this. It's going to be asymptotic. There's going to be a horizontal asymptote right here at y equals 0. Remember, this talks about end behavior, and so this end, as x goes to negative infinity, our function, or our y value, goes to 0. Doesn't actually get there. The other end of this graph does not have an asymptote, and so this one, as x goes to positive infinity, our y value goes to infinity. So that would be the end behavior of this graph, and we can tell that just by reading our graph. Okay. What about the domain of this graph? Well, our domain here is just going to be all real numbers, right? Because we go all the way to the left and all the way to the right. We just go really slowly, but this is still moving this way as well. And our range for this graph, well, our range, we do not go below 0, and we don't actually get to 0, so we are y greater than 0. We could also write this as y in 0, infinity. That would be another way you could write it. Either one is fine. Okay. When we're working with our exponentials, we're going to make sure to include most of this information when we graph. We're going to make sure we include where that horizontal asymptote is. We're going to include our domain. And we're going to include our range. We're going to make sure to discuss those 3 things every time we do this, because it's going to be related to some of the additional stuff we talk about this unit. So I kind of mentioned this at the beginning, that there's a difference between exponential and power growth. So power, what do we mean by that? Well, we mean when we have powers or exponents, so like x squared is power growth, x cubed is power growth, x to the 4th, etc. Those are all power growth things. Exponentials are like what we just talked about, 2 to the x. Let's use Desmos to help us do this. All right, so in Desmos, I'm going to put each of these in. Y equals 2 to the x. So that's what this one looks like. Let's color code as we go so you match what we see in our Desmos graph. So we've got y equal 2 to the x. Then we've got our power. Y equals x squared. It's going to be blue. And then we're going to do y equals x cubed. gonna be green. And we'll do one more. Y equals x to the 4th. It'll be purple. All right, so let's just take a look at what is happening here. So if we see all these things, they grow at different rates. So let's see if we can't squish this graph. There we go. And so we see that very quickly that red line gets on top of the blue line. It overtakes that blue line very quickly. Takes a little bit longer for it to overtake the green line. That green line is our x cubed, but right about 10, it goes past that, and then it's a lot taller, going a lot faster. And our last one, our purple one, takes a little bit longer, but if we sort of scroll, it overtakes our purple line as well. And so our red line gets above each of these power growths relatively quickly. I mean, it seems like it took a lot. We had to go really far up our y-axis, but we only had to go to 16 in x before our red line was faster. And by faster, I mean it's getting taller. Like our y value is getting bigger faster. And so our exponential growth is actually going to be faster than any polynomial. Or power growth. So let's put those in. All right. So we see our exponential graph, this red graph, overtaking our polynomials relatively quickly. I mean, even our biggest one, our x to the 4th, we only had to go to 16. That's not very big. So this exponential growth is much, much faster. That's what we need to know. So let's consider some applications of this. So which of the following options is better? We got option A and option B. So if we earn $1,000 each day for every day in the month of March, how much money would we have? Well, on day 1, we earn $100,000, which seems like a lot, right? On day 2, we earn $200,000. On day 3, we've got $300,000, right? Because we're earning an extra $100,000 every day. And so on the nth day, we're going to have n times 100,000. Well, there are 31 days in March. We're going to do 31 times 100,000. And we're going to get $3.1 million, which seems crazy. What about option B? Earning 1 cent on the 1st of March. So on March 1st, you get 1 cent, or $0.01. Then on the 2nd day, that's actually right, this is day 1, so it matches what we had above. On day 1, we've got 1 cent. On day 2, that's going to double, so we're going to multiply that times 2. So now I have 2 cents. Woohoo! All right. On day 3, we're going to double again. Now we've got a whole 4 cents. Making money. What about on day 4? Double that again. We've got 8 cents. Money in the bank. Guess it's better than nothing, right? What about on day n? How much money do we have? Well, to go from here to here, we did 0.01 times 2. From here to here, we did 0.02 times 2, but that's really 0.01 times 2 times 2. So this is 0.01 times 4. From here to here, we did actually 0.01 times 8 because we have 3 of these 2's. Multiply by 2, multiply by 2, multiply by 2. So we multiplied by 2 3 times. So on day n, we're actually going to multiply by 2n minus 1 times. So this is 0.01 times 2 to the n minus 1. Why is it n minus 1? Because we don't multiply by 2 on the first day. So we only have 1, 2, 3 for day 4. It's always one less. So this is what this looks like. So now we can figure out how much we have on day 31. And on day 31, we're going to have 0.01 times 2 to the 30th, because we have to do minus 1. And so we end up getting 1.0737 times 10 to the 7th. What does this mean? This means that we move our decimal place back 7. 1, 2, 3, 4, 5, 6, 7. So that means we have 10737 0 0 0 and 0 cents. Well, that is a whole $10,737,000. That's a lot. That's significantly more than 3 million. So I'd obviously want to choose option B. And so the question might be, when does that happen? When do we suddenly have more money than we did via option 1? So let's check that out. So when do we beat option A? Well, we can actually graph this, right? This one is going to be y equals n times 1,000, right? We wrote that down here. And this one is y equals 0.01 times 2 to the n minus 1, right? So let's graph those and see what happens. We're going to use x instead of n, so it looks a little bit nicer in decimals. So we got x times 100,000. Let's go. And we will have y equals 0.01 times 2 to the, and we got to put this in parentheses, otherwise it's going to force it down. So if we look at this, that black line, actually let's make it not black, let's make it purple. That black line is just looks straight, right? It looks so much faster than our exponential. So let's do the squeeze. We're going to squeeze. And we're going to go out and we're going to squeeze. Because we know we ended up with millions of dollars, so we got to get this in the millions. Ah, there we go. And so we can see now right there. So let's put this in here. That's like just past 29 days. Now realistically, and this is kind of a weird quirk, this is a what we call discrete concept. We're only getting money every day. So 21 or 29.17 days or 117 doesn't necessarily make sense. So what this means is after the 29th day. So that would be on March 30th, we beat out option A, right? But remember, option A was $3 million, and we ended up with 10 million, 3 times that. Does that make sense? Yeah, it kind of does, because we beat it out on the 30th, and then we have one more day, so we're definitely going to double. And on the 30th, we're already way past 3.1 million. And so it's that last day that makes all of the difference here. But notice, the only month that it would matter is maybe February, right? Where we've got 28 days. But otherwise, every other day in the month, every other month of the year has at least 30 days. So we're going to get more from option B. So let's do another problem. I like this problem, it's fun. A ream of 500 sheets of paper is 2 inches thick. So what's a ream of paper? If you think about like copier paper, those like big stacks of paper, that's a ream, right? It's got 500 sheets in it, it's 2 inches thick. So that means that we can say how thick is one piece of paper? How thick is one piece of paper? We can actually answer that. We have enough information now. if 500 pieces of paper, is 2 inches, then we just divide by 500 to get 1 paper is 2 divided by 500, or 1 over 250th of an inch. So we know how thick a piece of paper is. When we fold a piece of paper in half, it doubles its thickness. That makes sense, right? If you have a piece of paper and then you fold it in half, you now have that sort of second layer. So you've got basically what you've made is 2 pieces of paper that are connected on top of each other. So we want to know how many folds we need to make it with a single sheet of paper in order to reach a thickness of 1 mile. So what is the question asking? How many folds? That's what we want. How many folds to make with a single sheet of paper in order to reach a thickness of 1 mile? So we want how many folds to get 1 mile thickness. Well, we already have an issue because we don't have units that match. We've got a mile and inches, so we're going to convert this mile into inches. So 1 mile is 5,280 feet. So we're just going to do some unit conversions. Hopefully you remember this. So we want to do feet in a mile so that our miles cancel out and we're left with feet. So there are, in 1 mile, there's 5,280 feet. Then we got to convert feet to inches. So we want inches, feet's going on the bottom. There are 12 inches in 1 foot. And so then we're just going to be left with inches. And so we're going to multiply 1 times 5,280 times 12. And we get that this is 63,360 inches in a mile. All right, so we need to know that. All right, so now we need a formula. Well, we're going to approach it the same way we did A and B. So if we have 0 folds, we haven't done anything, we just have our sheet of paper. We are 1/250th of an inch thick. 1 fold, it doubles, times 2. We get 2 over 250 inches. 2 folds. Well, we're folding this, so this is going to double. That gives us 4 over 250. Keep going. We're looking for n folds. This is going to be our formula. Well, once we folded 1 time, we multiply by 1. Folded 2 times, we multiply by 2 twice, right? If we do 3 folds, we're going to multiply by 2 again, so that's 3. So we're going to end up with 2 to the n over 250. That's because the first fold is a multiplier. This is a little bit different than the way we did it before, because we're kind of counting at 0. So this is going to be our formula. And so we want to know when this is equal to the thickness. Let's call it T. Why not? But we want our thickness to be 63,360. So we're going to say 63,360 is equal to 2 to the n divided by 250. Well, we can multiply by 250, right? When we do that, we're going to get a very large number. This is 15,840,000. This might look like scientific notation on your calculator. 2 to the n. Now, how do we get rid of this 2? The answer is we don't know. We don't have an operation to undo this yet. We will actually learn it this unit, but we cannot actually do this. So what we can do, though, is use Desmos and our trusty table. So let's put this in. I'm actually going to put in, let's just put in this. 2 to the n, or to the x. All right, so let's hit this. We're going to hit our table. And so we're going to put in some numbers. Let's say like 10. Well, that's only 1,024. Not nearly enough. Let's add a 0. Oh, wow. We got to the 30th. That is way too many, right? Let's convert this. If we wrote this, this would be 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7. Yeah. So the 30th is way too high, so we've gone too far. Let's try like 50. Oh, that's 15. That's also too high, but we're getting closer. Let's go to like maybe 25. Oh, we're very close. We've got our 10 to the 7th, but we have 3.35. So let's go to maybe 20. Now we're too low. 22. Too low again, so we're going to go up. Let's say 23. We're very close now, right? But we're still at 10 to the 6th. So if we go to 24, this is going to be it. We're a little bit higher, 1.6. But remember, we can't do a part of a fold, so it's either 23 or 24 folds. And so this is going to be 24 folds. So it only takes 24 folds of a piece of paper to go a mile. So your paper is a mile tall now. What if we wanted to go to the moon? That's about 240,000 miles. Well, the only thing we're changing is this value, right? Our formula otherwise remains the same. So this is going to look like 2 to the n divided by 250. Then we're going to go 240,000 miles, which we need to convert to inches, but we know how many inches are in a mile now, right? That's 63,360. So it's going to look like this. So when we multiply, we get a very large number. That's not surprising. It's a lot of miles, right? It's going to be 1.52064 times 10 to the 10th, right? And so we don't actually need to move that 250. Let's just make the adjustment here. So let's use 2 to the x divided by, make sure we get out of the exponent, divided by 250. And so we want to know, when does this get there? So we're going to use our table. Well, we knew it took 24 to go a mile, right? And so if we look at it this way, we see, yeah, that's just about a mile. And so how many do we think it's going to take to go 240,000 miles, or 240 times that distance? Well, maybe we think it's a really big number. Let's try like 100 again. Well, if we look at 100, we are to the 27th. That is way too far. Let's try like 50. Still too far. We're getting much closer, but we're 10 to the 12th now. Let's try like 30. 30 is not nearly enough, right? What if we did 40? 40 is really close. Our exponent is just 1 off. Let's try 45. Not quite. Now we're a little bit too far. 42. That looks very close. It's just slightly over. So let's go down 1. If we go to 41, we're not far enough. So we got to go all the way to 42. So n is 42 folds. So this is actually less than twice what it took to go to a mile. Right, because it took 24 to go to a mile, and double that would be 48. So we're just under twice what it took to go to a mile. So what we need to learn about this is that exponential growth is really, really fast, and thus usually unrealistic if unchecked, right? So it doesn't always make sense to use exponential. Sometimes it makes a lot of sense in terms of like modeling a population over a short period of time, but normally this long-term behavior just isn't realistic. We're not really going to infinity in a lot of realistic things, but it is very good for short-term modeling. And we see lots of exponential, especially exponential decay. We're sort of getting smaller is really big. So another question we may ask is, how wide is the paper? right? If we want to go to the moon, we need to be able to stand on it, right? Well, let's assume, we're going to round up. Let's assume, so we have a nicer number, that our paper is 12 inches. So 0 folds, and our paper is 12 inches long. After 1 fold, how long is our paper? Well, it gets cut in half, right? Once we fold, because we're folding it in half, so now it's 6 inches. What about 2 folds? Gets cut in half again. Now it's 3 inches, etc. And so after n folds, how big is it going to be? Well, 1 fold, we multiply 12 by 1/2. 2 folds, we're multiplying 12 by 1/2 twice. So we're going to multiply 12 by 1/2 to the n. So this is what this one's going to look like. And so we know already that 1 mile is 24 folds. So how wide is it going to be? That's going to be 12 times 1/2 to the 24th. And then when we go to the moon, right, that makes 42 folds. And we get 12 times 1/2 to the 42nd. Well, let's look at what those numbers are. So we've got 12 times 1/2 to the 24th. So when we fold it for our mile, our paper is, let's say, 7.15. I'm going to ignore the rest of the times 10 to the -7th. Let's go ahead and get our moon. So this one is 2.73 times 10 to the -12. All right, so let's look at what that means. So that means we've got 0 point, and then we've got 6 zeros. 1, 2, 3, 4, 5, 6, 7, 1, 5 inches. That is tiny. It's even worse here. We've got 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 273 inches. Could you stand on this? Absolutely not. This one, both of them, it's like, can you even grab this? Is this even realistic? No, right? And it gets to the point where our paper physically can't necessarily fold it anymore. So as our paper gets really, really long and really, really tall, it also gets really, really small and really, really wide. It basically gets infinitely long in one dimension and infinitely small in the other dimension. So basically it just disappears. So let's do a little experimentation. This is sort of our general formula for exponential equations. Or exponential functions. So let's take a look in Desmos at what happens when we graph this. So we got y equals a times b to the, and then I'm going to put in x minus h plus k. We're going to add all those sliders. We're going to make b, let's make it 2. And then we're going to play with the rest of them. All right, so let's look at A. Let's look at what happens when we do that. So what's it doing? It's making it taller, right? And then it flips it and makes it taller. So it does the exact same thing it did before. So A, this is our vertical stretch component. Right? It's going to make it taller or shorter, and it's also going to flip our graph. Right? If we look at H, let's reset this back to like 1. If we look at H, what does it do? Well, it might look like it's making our graph wider, but really all it's doing, oh weird, all it's doing is moving our graph to the left and right. And it becomes a little bit more clear when we zoom out. That shouldn't be surprising. It's our term next to our h, and we're adding or subtracting, so this is our horizontal shift. Notice it has no impact on where that horizontal asymptote is. Doesn't do anything. Asymptote is exactly where it was when we moved this. Let's make it 0. All right. And then let's look at k. So what happens when we move k? K is moving our graph up and down, right? This is our vertical shift. Should make sense because it's that outside number. And this tells us exactly where the horizontal asymptote is. So our horizontal asymptote is y equals k. Now, we're going to assume b is greater than 0, and why do we do that? Well, let's look a little bit closer at b. b, if I make it less than 1, flips this, right? So if b is less than 1, but still greater than 0, we get our graph that looks like this, right? If our b value is greater than 1, our graph looked like this. So we get a little bit different behavior. This is actually a horizontal flip, and we'll look at sort of why that is later. We get this horizontal flip. What happens when we make a negative? It disappears. Does that mean it doesn't exist? No, because notice that Decimus has not yelled at us at all. And if we make a chart, suddenly we can see our graph. Look at this. Let's put in some more numbers like 3, 4, 5. Oops. I guess that's all it wants me to do. There we go. 5. Let's put in a little bit further back. Let's do like -3, -4. All right. And so our graph looks like this. It's just a whole bunch of points, which is kind of weird, right? Let's put this in here. And so our graph looks like this. And so what's happening is that when we have even powers, right, if we have a negative number to an even power, we get a positive number, right? If we have a negative number to an odd power, we get a negative number. So we see this sort of oscillation happen. And that oscillation happens, and then we also have that if we have a negative number to the 1/2 power, that's the same thing as the square root of a negative number, which is imaginary, and thus not graphed. So we actually have places where we don't graph anything. And so this is actually true for any number over 2 exponent. So we have a lot of points that are missing, and then we have a lot of points that sort of jump and oscillate back and forth. And so if you remember from our last unit, we had this idea of discontinuities, right, where we would jump from point to point. And so this graph is an example of something that is infinitely, well, actually, let's say it this way. This graph is discontinuous everywhere. None of these points touch. There's no continuity anywhere in this graph. And this is not something that happens sort of in the natural world, really, so we don't worry about this. We're more interested in things that have a positive base, right? And so this b is called the base of our exponential. Okay. So for example, let's look at this graph. We've got y equals -3 times 4 to the x plus 1 minus 2. So we already know we're going to have a horizontal asymptote at y equals -2. Let's go ahead and graph that. So So this is our horizontal asymptote. The other big indicator here is this -3. This means we flipped vertically, which means we're going to be under the asymptote. That means we are going to live down here with this graph because we flipped over it. And then the last thing we're going to look at is this base. Our base 4 is greater than 1. So we expect normally this would look like this, but it's been flipped. So our graph should look something like this. We can go ahead and say our domain. Our domain is going to be all real numbers because it is for all exponentials. Our range we can also already say is going to be y less than -2 because of what we decided based on our leading coefficient and that horizontal asymptote. If we plug in a couple points, we could actually graph this pretty quickly, or we could use Desmos. And so we are graphing y equals -3 times 4 to the, and we're going to use parentheses so this whole exponent goes in the exponent, x plus 1 minus 2. And so our graph looks like this. Has a y-intercept of -14, so it's pretty far down there. So we're going to look something like this. Right? This is maybe a little bit of a bad drawing on my part, but more or less like that. So you should remember from back in the day, exponential graphs aren't entirely new to us. We have two options, growth or decay. And so growth means that we're going up, right? This is what happens when our b value is greater than 1. Our decay is when we're going down. And so this happens when our b value is less than 1, but still greater than 0, right? And so in our paper folding problem, this was the height of the paper was exponential growth, but the width of the paper was experiencing exponential decay. So this was going away, well, this was getting really, really big. And so we can actually see, let's talk about why this 0, b between 0 and 1 is actually an example of exponential decay, right? Because if b is a fraction, is what that means, a fraction less than 1, then we could rewrite it as a negative exponent, right? Because this would be y equals 1/2 to the x. That's what our negative exponent does, right? It basically makes it a fraction. Because really we might write y equals 2 to the negative x as 1 over 2 to the x. But 1 to any power is 1, so we can actually write this as 1 over 2 to the x. So we actually have exponential decay and exponential growth sort of have an opposite option. This is when the x coefficient, let's say bx, let's not use b because we already used that. X coefficient is positive here. Same thing over here. This happens when our x coefficient is positive. If our x coefficient is negative, then exponential growth would happen if b is less than 1 and greater than 0. So let's look at an example. If you had y equals 1/2 to the negative x, that's really 2 to the x. That's growth. Similarly, over here, if our x coefficient is negative, then this happens when our base is bigger than 1. Let's do an example that's slightly different than this one. If we had y equals 4 over 3 to negative x, that would be 3/4 to the x, which is decay. So we need to be careful. There's sort of two things we need to look at for exponential growth and decay. All right. If you're interested, Mythbusters, which is a program that sort of looked at myths, did this paper folding problem where they tried to actually fold a piece of paper more than 7 times. You can check that out using the link in our notes. Can't necessarily fold it anymore that many times. And so the taller it gets, why? go take this somewhere else.